Hello, my name is Andrew Kerr. I'm joined today with Chris Cheka. Today we'll be providing an update on the CUTLASS project, specifically the new CUTLASS Python API. We'll also cover enhancements to CUTLASS 2.x, as well as a preview of CUTLASS 3.0, the next major revision of the CUTLASS project. I'd like to acknowledge the vibrant CUTLASS GitHub community and pay special thanks to the many folks who have contributed new functionality, performance optimizations, bug reports, and other feedback. I'd also like to acknowledge the hard work by the CUTLASS engineering team, particularly Hai-Chang Wu, Pradeep Ramani, Aniket Shivam, Vijay Thakur, Jin Wang, Honghao Liu, Ethan Yan, Shang Zhang, Jack Chen, Patrick Liu, Xiaodong Chen, Yu Zhai, Jack Hossain, Dustin Boslick, and Dwayne Merrill. Finally, I'd like to acknowledge the great work by the CUTLASS product management team, Matthew Nicely and Tim Costa. CUTLASS is a CUDA C++ template library for deep learning and high-performance computing. CUTLASS provides optimized CUDA C++ templates for matrix computations at all scopes within the CUDA execution model and all workload scales. CUTLASS provides pre-baked device-wide computations for GEM, convolution, reductions, element-wise computations, and more for all data types supported by NVIDIA GPUs on all shipping architectures. CUTLASS has a layered software architecture so that components used to implement the device-wide operations are available as reusable standalone components in other contexts. These include collective operations like pipeline matrix multiply, epilogues, and iterators over convolution matrices. It also includes thread level and architecture intrinsic operations for wrapping architecture-specific PTX instructions in a uniform template design space. CUTLASS is open source. It's available in the NVIDIA organization's GitHub page under the new BSD license. The latest revision of CUTLASS is CUTLASS 2.11. It has been the subject of previous GTC presentations from 2018, 19, 20, 21, and 22. These describe the ingredients of an optimized GEM, describe the details of programming NVIDIA Tensor Cores on Volta, Turing, and Ampere architectures, as well as provide details for an efficient implicit GEM convolution computation in CUDA. CUTLASS is a collaboration of the CUDA compiler and NVIDIA research teams to provide the best possible performance across the board. Each minor version of the CUDA toolkit has enabled new optimizations affecting specific classes of kernels. CUDA 11.3 offered a tremendous performance boost for Tensor Core GEMs. CUDA 11.6 offered speedups for single precision CUDA and Tensor Core GEMs. And then finally, the best possible performance is expected from CUDA 11.8, the latest shipping toolkit. The agenda for this talk is to describe the roadmap of CUTLASS and then to dive deep into each of the new components under discussion. CUTLASS is aligned with the release schedule of the CUDA toolkit. CUTLASS 2.10 released in August 2022, and it adds the new CUTLASS Python interface. It also includes feature enhancements and performance optimizations for group GEM, fused kernel compositions for computing softmax and layer norm for multi-head attention applications, as well as grouped and depth-wise separable convolution. CUTLASS 2.11, planned for release in October 2022, is aligned with CUDA 11.8. This features the enablement of the new NVIDIA Hopper GPU architecture. And CUTLASS targets this by providing a 2x speedup for double precision tensor cores and interaction with the new FP8 numeric type. CUTLASS 2.11 also supports StreamK, a dynamic scheduling algorithm that enables a single tile size to meet or exceed the performance of an ensemble of multiple kernels and multiple tile sizes, all without a complex heuristic. Later this year, CUDA 12.0 will provide direct access to NVIDIA Hopper's 4th generation tensor cores from within CUDA. We're offering a preview release of CUTLASS 3.0 to showcase programming Hopper tensor cores and to present Qt, a new programming model for implementing tensor-valued computations in CUDA. CUTLASS Python. CUTLASS Python is intended to bridge the gap between CUDA C++ templates and user environments in Python, including PyTorch, NumPy, QPy, TensorFlow, and Numba. In this figure, the left-hand side shows a typical CUTLASS GEM instantiation. A number of template arguments are used to specify the data types, layouts, and tuning parameters for an optimized GEM. This is then compiled and added to a dispatch table to enable an application to pick the right kernel and launch it at the appropriate time. However, all of this is in C++. Python users expect a certain level of abstraction so that a basic matrix computation can be lowered onto the appropriate kernel. CUTLASS Python is intended to support that. The architecture of CUTLASS Python is to enable a Python user to interact with CUTLASS during both compile time and runtime. During compile time, the Python client specifies the description of an operation. Here they're wrangling the data types, layouts, alignment, requirements, tile sizes, and other details to specify a gem or convolution kernel in CUTLASS. This is then used to drive a code emitter, which constructs a CUTLASS kernel template instantiation. Then it invokes the host and device compilers to compile this kernel into an executable workload. All of this makes heavy use of the CUTLASS C++ template library. The results of compilation are placed in an SQLite-based code cache. Now, during runtime, the user provides tensors in a variety of recognizable formats, including Torch's tensor descriptor and NumPy's ND array. Argument wrappers within CUTLASS Python adapt these native tensor descriptors to a tensor reference that is expected by CUTLASS. A memory manager and a runtime are used to select the appropriate kernel, manage temporary workspaces needed by that kernel to implement the computation efficiently, and to dispatch it as needed. Here we have a complete CUTLASS Python example. On the left-hand side, we have interaction with the CUTLASS Python API to define the math instruction, in this case, a 16 by 8 by 16 tensor core operation. We define the tile size, in this case, a 128 by 128 by 32 CTA. We describe the data types and layouts of tensor valued operands. We define the epilogue functor, in this case, linear combination. On the right-hand side, we put these ingredients together to form the complete operation, in this case, a universal gem in CUTLASS. And then we invoke JIT compilation by adding the operation to a module. Then at runtime, we use the CUTLASS Python API to adapt NumPy tensors that are created in device memory and wrap those in a CUTLASS gem argument structure. Then we pass this to the CUTLASS operation and launch the grid. That's it. That's all that's needed to instantiate a CUTLASS gem. Because CUTLASS Python uses CUTLASS C++ under the hood, we don't really expect any performance variation between the two. In this example, we're profiling two-dimensional convolution for deep learning training on the NVIDIA A100 GPU. Here we can see both forward and backwards passes for convolution performance across the different layer sizes of ResNet 50. And as predicted, performance is almost identical. The same holds for CUTLASS Gem. Here we're showing different different layer sizes in the BERT workload, and performance is virtually identical. CUTLASS Python can be used not just to define basic gem and convolution kernels, but also to specify fuse operations according to several well-known design patterns. Fusion within the main loop enables the kernel to perform element-wise computations, simple reductions, and simple broadcasts of data as it's being fetched within the gem or convolution main loop. These have a variety of recognizable use cases, some of which we'll talk about later today. Fusion within the epilogue enables a kernel to perform some computation on the result of a gem or convolution before it is stored out to memory. This includes fetching additional tensor or vector operands, reshaping the data, including broadcasts, performing reductions, and performing element-wise computations. These are all quite recognizable. Finally, CUTLASS Python enables the fusion of back-to-back gem or convolutions within a single CTA. Now, these have several hard constraints related to problem size, but if a problem size can fit, CUTLASS Python enables the creation of a sequence of gems within one kernel. In this section, we will describe enhancements to CUTLASS 2.x, starting with fusions with gem. Layout transformations are common operations in deep learning workloads. In this example, we have a gem followed by a layout transformation, which permutes the strides of tensor indices. This requires storing the data to global memory by the gem, fetching it by a second kernel, which then stores a transpose representation to global memory. The additional data movements by the layout transformation kernel add to the overall runtime and can be avoided by fusing the transpose operation with the gem. CUTLASS 2.10 provides a gem with permute function, which applies a user-defined layout to map the logical tensor coordinates of the output tensor to arbitrary positions in global memory. Permutation functions required by this use case correspond to unique layout functions. This simple enhancement can enable the gem to store data directly in the desired tensor layout and may be nearly as efficient as the original gem if the contiguous dimension is not reordered. A micro-benchmark compares the performance of batch gem fused with a permutation function with the unfused case requiring 2 kernels. The problem size is typical of a gem-intensive DL workload, as is the layout transformation function in question. As the results show, the permutation kernel contributes a significant fraction of the overall runtime. In contrast, the batch gem fused with permute is only marginally slower than the original gem. The overall speedup is 1.9x. Layer normalization is another common operator within DL networks. It is defined as subtracting the mean of slices of a tensor, then scaling by the standard deviation, followed by an additional scaling operation and bias add. Computing the mean and variance requires a reduction, which, implemented naively, loads the entire tensor from global memory. We can decompose the normalization computation into a partial reduction step, a final reduction step, and an element-wise step. The partial reduction can be fused into the epilogue of the previous gem. This computes the sum and sum of squares of the elements output by the gem and stores the result in a vector. This vector is relatively small compared to the overall size of the output matrix Z. The second kernel performs the final summation to compute the mean and variance. Then it rearranges terms to form the mean and reciprocal of standard deviation. This is written to a vector in global memory. The element-wise operations can be fused to the input of the subsequent gem kernel. These perform scaling and bias add on the input elements prior to dispatching them to the tensor core data path within the main loop of gem 1. Fusing gem, layer norm, and gem into this 3-kernel sequence reduces overall memory bandwidth demand. In these micro-benchmarks, there is a resulting speedup of over 10% for each workload. The strategy of fusing reductions within gems can be taken further to fuse the calculation of softmax within the epilogue of a gem. Softmax requires 2 reductions to be performed, the first to compute the maximum value of each column, and then to compute the sum of exponentials. Subsequently, element-wise operations compute exponentials and then scale the output tensor. The same strategy of fusing the partial reductions into the epilogue can avoid extra reduction kernels to compute the softmax operator. The result of fusing softmax with gem is favorable. This example shows several benchmarks and illustrates a substantial speedup for each workload. Softmax can be combined with the CUTLASS grouped gem operator to compute fused multi-head attention. CUTLASS's group gem implements the concept of batch gem, where each matrix product within the batch may have a unique problem size. Group gem has been the subject of several optimizations since its initial release in CUTLASS 2.9. Here we have a complete fused multi-head attention example that applies the CUTLASS group gem implementation. And it's fast. CUTLASS's fused multi-head attention example combines these ingredients and showcases a speedup of 6.25 times faster than a naive PyTorch implementation. The benchmark application is available in the CUTLASS examples on GitHub. In this section, I'll describe the implementation of grouped and depth-wise separable convolution. Grouped convolution generalizes the familiar convolutional operator by partitioning filters into filter groups. Each filter group convolves a subset of the input tensor channels. The expression in the figure defines the group convolution operator in detail. Notably, the number of multiply adds performed is decimated by G, the group count. Thus, grouped convolution provides a convolutional operator that significantly reduces arithmetic intensity and offers a savings in model size by reducing the number of channels per filter stored and learned. Group convolution can be implemented efficiently for GPUs by extending the existing implicit gem convolution pipeline. In this figure, we have illustrated a 2x2 convolution using the familiar gem L-shape. The activations tensor at the center bottom of the figure and the filters tensor is on the right. The output tensor is partitioned into 8 CUDA thread blocks, which compute independent output tiles. The indices R, S, G, and C show how each thread block iterates over the gem inner dimension and decomposes the iteration index into the logical indices of the convolution operation. Notably, the 16 channels of the activations tensor are striped over the 4 groups for this problem. Group indices are color-coded, and the filters tensor shows the relationship between the filter groups and the inner and outer gem dimensions. CUTLASS's implementation defines a mode which maps one CTA to one filter group. This figure zooms in on the workload of 2 individual CUDA thread blocks, CTA0 mapped to the filter group 0, and CTA2 mapped to filter group 1. We can see that CTA0 only computes channels that correspond to filter group 0, namely channels 0, 4, 8, and 12. CTA2 shows a similar pattern. Each linear index of the gem inner loop corresponds to one main loop iteration. From the figure, it is plainly apparent that the number of main loop iterations has been decimated by a factor of 4 group count. This is a significant savings in flops. Not all workloads support this type of mapping. If the number of filters per filter group is smaller than the thread block tile, the thread block will spend much of its time multiplying by 0. This is wasteful. We can improve overall utilization by defining a mapping mode in which one CUDA thread block computes the result of multiple filter groups. In this example, CTA0 is mapped to filter groups 0 and 1. The resulting computation is illustrated and shows a 2x reduction in the main loop iteration count. This is certainly a worthwhile speedup. It also hints of the possibility of further optimizations to leverage block sparsity within each main loop iteration. The CUTLASS does not take advantage of that at this time. The interface of CUTLASS's group convolution operator is similar to the existing dense implicit gem implementation. The template interface identifies a unique default conv2d grouped fprop operator. An extra template argument selects between the single group per CTA behavior or the multiple filter groups per CTA behavior. This must be chosen at compile time. The argument structure is unchanged. The number of groups is interpreted as the ratio of the input channel count to filter channels. All other runtime arguments are also unchanged. Depthwise separable convolution is the extreme form of group convolution in which the number of filter groups matches the number of input channels. Each filter has a channel count of 1. When viewed as a matrix product, depthwise separable convolution results in a diagonal matrix of the filter's operand. The CUTLASS implementation takes advantage of this by only fetching the filter elements on the diagonal from global memory and into the register file. The resulting matrix product of the convolution matrix by a diagonal matrix is computed using the existing CUTLASS warp level matrix multiply operation. Depthwise separable convolution maintains the existing template interface in CUTLASS. A unique kernel level operator is utilized. This workload has much lower compute intensity and is memory bandwidth limited on most GPU architectures. Consequently, to ease the implementation, it does not use tensor cores, which would not offer any speedup. It targets CUDA cores and uses the existing SGEM formulation. Arbitrary data types are supported, and these are computed to the internal compute data type within the kernel's main loop. Next, we'll describe StreamK, a dynamic scheduling algorithm for maximizing expected performance within a single gem tile size. Existing gem and convolution implementations perform a spatial partitioning of the output matrix into tiles, which are then mapped to CUDA thread blocks. A CUDA grid is launched for each thread block, which executes in parallel on the GPU. This strategy has a straightforward implementation in software, but it suffers from quantization efficiency. If the number of thread blocks launched is not an integer multiple of the number of SMs, the GPU is partially occupied. Average utilization is diminished as the machine is only partially utilized during the last wave of thread blocks. This slide illustrates a 3x3 grid of 9 thread blocks launched on a hypothetical machine with 4 SMs during 3 waves. The first 2 waves saturate the GPU. However, assuming all thread blocks have the same runtime, the final thread block runs on a single SM while the rest remain idle. This results in a diminished utilization. One recourse for partial thread block waves is to instantiate multiple tile sizes with different quantization inefficiency and then select the best kernel to launch. This typically requires a complex performance prediction heuristic and necessitates many kernels, not all of which will ever be run by a given application. StreamK attempts to minimize quantization efficiency with a single tile size by considering the entire outer loop iteration space. Specifically, StreamK linearizes all thread blocks and all main loop iterations within a thread block. This figure shows an example with 4 main loop iterations per output tile. Linearization can be partitioned over the given SMs available in the machine. A CUDA grid can launch strictly as many thread blocks as there are SMs, which implement the main loop iterations of all covered thread blocks. In the example, 36 main loop iterations is perfectly divided by 4 SMs. In practice, the worst case error is just the duration of computing one main loop iteration. By definition, this is less than the duration of one output tile, which consists of one or more main loop iterations. Thus, StreamK achieves load balance. However, it's clear that some output tiles are computed by multiple SMs. In the example, thread blocks 2, 4, and 6 are shared by 2 SMs. A fix-up operation is required to store the partial results to a device-side workspace and reload it by the next thread block, which may consume it. This fix-up operation can be performed deterministically, and it may be sequenced to enable the thread blocks to execute concurrently prior to exchanging data. This figure shows a collection of 4 thread blocks executing concurrently on 4 SMs. Each thread block is computing multiple output tiles. The fix-up and carry-out operations are performed to handle output tiles split across SMs. It must be noted that the number of fix-up operations, as well as the total buffer space required, is proportional to the number of concurrent thread blocks needed, not the problem size. Thus, a constant buffer space may be allocated, whose size strictly depends on the overall occupancy of the GPU. StreamK can be considered a generalization of SplitK, which partitions one output tile into multiple CTAs, but does not attempt to load balance to minimize quantization efficiency. The implementation of StreamK adds an additional outer loop to implement the persistent thread block model. Scheduling logic is implemented to determine the next output tile to compute, and fix-up logic is implemented to decide whether to store the partial results to the device workspace or fetch them and accumulate them prior to computing the final output. The existing pipeline main loop and epilogues from CUTLASS are used virtually unmodified. StreamK may be compared to an ensemble of multiple kernels with a selection heuristic. In this experiment, a set of 4096 randomly chosen problem sizes with a logarithmic distribution are evaluated with CUTLASS, which itself has an ensemble of 20 kernels per data type. This is compared with one StreamK tile size of 128 by 128. The plots illustrate tensor core utilization as a function of arithmetic intensity. On average, StreamK offers a 10% speedup. It offers a 5.4x best case speedup and visibly improved performance relative to the roofline, which models the theoretical peak. There is some slowdown in the worst case, though this can be improved by addition of a small number of additional tile sizes. No elaborate kernel selection heuristic is required, and the total number of kernels is dramatically reduced. StreamK is exposed in CUTLASS's template interface by tagging the StreamK kernel with a unique thread block swizzling function, threadblock swizzle StreamK. This can be passed as a unique tag to the existing CUTLASS kernel level gem. The runtime argument interface is extended with 3 additional parameters: DP tiles, indicating the number of output tiles mapped to independent thread blocks, mirroring the current static scheduling algorithm; StreamK blocks indicates the number of thread blocks which perform dynamic load balancing; and then available SMs, which controls the number of concurrent persistent thread blocks to launch. Each of these may be given a default value, which triggers an internal heuristic. This heuristic was used to present the results from the previous slide. We plan to enable StreamK by default to enable the default CUTLASS build to offer the best performance possible without instantiating all possible tile sizes. Next, we'll describe how CUTLASS 2.11 enables new features in the NVIDIA Hopper GPU architecture. NVIDIA Hopper is NVIDIA's next major GPU architecture. Hopper delivers a 2x architectural speedup over the NVIDIA Ampere architecture. Mixed precision floating point matrix computations are accelerated by a factor of 2, clock per SM. NVIDIA Hopper also implements 2 additional floating point types, 8-bit floating point. These are accelerated by hardware support for numeric conversion and by specialized 4th generation tensor cores. More architectural features are needed to implement optimal gems and convolutions, to avoid being bottlenecked by data transfer and stalled on barriers. These features are described in more detail in the NVIDIA H100 GPU architecture white paper. CUDA 11.8 is the first CUDA toolkit version that supports NVIDIA Hopper. However, not all features in Hopper are accessible to the CUDA programmer in this version. Exposing these remains the subject of future CUDA toolkit releases. Double precision tensor cores and support for FP8 data types are accessible, and these are targeted by CUTLASS 2.11. CUTLASS kernels targeting existing functionality exposed in NVIDIA Ampere and prior architectures remain fully accessible and efficient. NVIDIA Hopper accelerates double precision matrix multiply accumulate via a larger MMA shape. The distribution of data among threads and registers extends the existing pattern exposed in the NVIDIA Ampere architecture. In this illustration, 32 threads within a warp are mapped to the 16 by 8 by 4 problem shape implemented by the Hopper double precision tensor cores. Thread 0 contributes 2 double precision elements for the A matrix, 1 double precision value for the B matrix, and is mapped to 4 double precision accumulators. The spatial arrangement is depicted in the figure. The PTX syntax is shown on the right side of the slide and follows the structure of the existing exposure of MMA.sync. CUTLASS's double precision implementation for Ampere internally structures the MMA operations as 16 by 16 by 4. This enables 128-bit vector loads to fetch 2 consecutive elements of the A and B operands from shared memory and issue the appropriate number of MMA sync operations. Thus, we can reuse nearly all of the CUTLASS implementation with minimal changes to the template structure. This slide shows the definition of a device-wide double precision gem operation for the NVIDIA Ampere architecture on the left and for the NVIDIA Hopper architecture on the right. The only syntactic difference is to specify the 16 by 8 by 4 instruction shape for NVIDIA Hopper. The runtime interface remains completely unchanged. CUTLASS 2.11 implements real and complex value double precision, gem, and convolution. NVIDIA Hopper implements 2 new 8-bit floating point data types, E4M3 and E5M2. The names refer to the number of exponent and mantissa bits within each operation. As mentioned, CUDA 11.8 does not directly expose tensor core operations capable of consuming FP8 directly. This will come in a future CUDA toolkit release. It does, however, expose hardware-accelerated convert and pack instructions. These are capable of converting a 4-element vector of FP8 elements to FP16 and vice versa. It is also capable of converting 4 FP32 elements to FP8. CUTLASS 2.11 takes advantage of hardware conversion capabilities by implementing FP8 fast math gem kernels. These support FP8 storage in global memory and perform type conversion to FP16 as the data is fetched from shared memory into registers. Thus, it is accelerated by Ampere-era tensor cores, albeit slower than native Hopper tensor core acceleration. It does, however, enable the use of 8-bit storage and the associated reductions in model sizes. It also enables CUDA developers to write kernels that may be interoperable with computations in cuBOS and cuDNN, which take advantage of native Hopper 4th-generation tensor cores. Next, Chris Cheka will describe the Qt layout functions and a preview of CUTLASS 3.0, the next major release of CUTLASS.
Thanks, Andrew. CUTLASS 3.0 is an exciting new way to compactly write dense linear algebra kernels. It's based on layout functions in a new library we call Qt, which also defines a formal algebra over those layout functions. This lets us represent the layouts of threads and data independently, partition data across threads seamlessly, and use tensor cores more effectively than ever before. In this section, I'll introduce the layout concepts and demonstrate how we can use those in developing CUDA kernels. Qt layouts are powerful function objects that map logical coordinate spaces to storage indices. A layout is made out of a shape and a stride, as you might expect, but on this slide I'm showing a logically 4x4 matrix whose data is neither row major nor column major. On the left, I'm showing 3 logical coordinate spaces, which can all be mapped into each other using the shape information. These are all valid ways to index into the layout. On the right are the storage indices for a corresponding data array. And again, note that this is neither row major nor column major, it's something in between. The representational power of Qt layouts is quite broad. As an example, I'm showing a 3-layer Morton order layout function built up from smaller layouts here. There are various ways to ask a layout about its shape. This layout has 64 total elements arranged in an 8x8 matrix. As shown, we can index into this layout like a vector, like a matrix, like a tensor, using any of the coordinate spaces that this layout admits. Similarly, we can slice into the layout to get sublayouts, and I'm showing subvectors and submatrices here. Although we won't deep dive into it here, there's a formal algebra defined over Qt layouts. That means that we can compose 2 different layouts. We can take the inverse of a layout. We can find the complement of a layout. And from these 3 operations, we can define higher order operations, such as taking the logical product of 2 layouts or the logical division of 2 layouts, and very fancy tiling operations and partitioning operations. In Qt, we use layout for both threads and data, and that allows us to replace every single iterator in CUTLASS with a layout instead. Rather than performing complicated index arithmetic to compute the layout of threads and data in some of these images that you see, and making sure that those iterators agree across code boundaries, Qt layouts manage the bookkeeping for us and provide powerful correctness guarantees. As a further example, I want to show you our new programming model for tensor cores that uses layouts for the majority of the heavy lifting. On the left, we have the new DMMA instruction that will be available on the upcoming Hopper architecture. It's simply wrapped in a function object and knows nothing about the logical structure of the instruction. On the right, we record the MMA traits, every piece of meta information about the instruction that a programmer needs to know in order to use it. This includes the logical shape, the threads that will be involved, and the layouts of the threads and the values in the A, B, and C tiles. With the PTX instruction and its full metadata, we're ready to create an MMA atom. An MMA atom is simply the combination of the PTX instruction and its complete metadata encoded in the traits. Here, I'm constructing the new Hopper DMMA atom and outputting a human-readable version of the metadata. This should look familiar to what was shown by Andrew a few slides back. An MMA atom can be called and executed, but we need to pass it registers to compute on. We'll get there in a moment after we make our problem bigger and more complicated first. One warp is fine to compute with, but I want 4 warps. Specifically, I want 2x2 DMMAs in a column major order. Essentially, I'm taking the product of the DMMA layouts with the layout of MMAs that I want. This could be row major, column major, something else, 2x2, 2x4, 3x2, whatever. Again, I'm displaying a human-readable version of the function we are creating. Before we continue, if you look very closely at the previous layout, you might see something a little undesirable, which is thread 0, and in fact all threads, are accessing elements in A that are not adjacent. For vectorization opportunities and to make our lives easier down the road, I'm just going to go ahead and permute the rows of this operator that we're constructing so that thread 0 and all threads are accessing adjacent elements. To perform this permutation, all we're doing is applying another Qt layout. Now we're ready to use the MMA. First, we ask for this thread slice of the tiled MMA. Here, I've highlighted thread 24. It owns a 2x1 piece of A, a 1x1 piece of B, and a 2x2 piece of C. Now all we need to do is feed this data. To feed it data, all we need to do is wrap data pointers into Qt tensors and call gem. I've used simple column major layouts, but again, these layouts can be anything, and that's the key. Column major, row major, any Qt layout in between, even swizzled data layouts. It seems like there's black magic going on here, so let's peek into that gem function real quick. Inside that gem function, the thread slice of the MMA is used to partition each tile's data. The thread A, thread B, and thread C tensors are subtensor views of the A, B, and C data. These have the correct shape and order of elements for processing by the MMA. Tensors RA, RB, and RC are register tensors that have the same shape as the partitioned views. Then, all that needs to be done is to copy this thread's subtensor of A and B into their register tensors and call the MMA object with a classic 3-loop gem. When we're done, we can simply copy the registers back to this thread's view of the C tile. And that's a gem. Similar strategies can be applied to other portions of CUTLASS. In analogy to the MMA atom, tiled MMA, and thread-sliced MMAs, we can build copy atoms, tiled copies, and thread-sliced copies to apply complicated copy operations, such as LDSM, automatic vectorization from shared memory to registers, aligned global memory loads from global memory to shared memory, or global memory to registers, etc. So that's an overview of Qt and how we use it throughout CUTLASS 3. And now I'd like to talk more about how the CUTLASS 3 API is going to change in order to use Qt in the backend. The CUTLASS 3.0 compute hierarchy is similar to the CUTLASS 2.x hierarchy, but with a few middlemen cut out. We've already discussed the atom level, the level of individual PTX instructions and their associated metadata. Atoms can be math or copy instructions and can involve one or more threads. Above that is the tiled MMA and tiled copy level, which are arrangements of these atoms to form collective operations. At the collective level, collections of threads work together to execute many math and copy instructions, and it's at this level where we are actually writing the speed of light pipelined main loops for GEM, and it acts as the composition points for main loop fusion or epilogue fusions, etc. At the kernel level, we provide points for composing collective main loops with collective epilogues or collective prologue operations. At the device level, we provide kernel configurations for speed of light common gems and launch utilities. These configurations include the tiled MMAs themselves, the optimal Qt layouts for shared memory, global memory vectorization and alignment configurations, etc. The nice thing about this is that because the Qt layouts contain their own state and representation, we can customize these layers in the hierarchy while preserving the composability with other layers. And furthermore, because we can inspect these layouts, we can provide much better static checking at every layer to ensure certain compatibilities, such as your A and B tiles both have the same K dimension. CUTLASS 3.0 has a device compatibility API very, very similar to 2.x. We would like it to be backwards compatible with CUTLASS 2.x and provide default gem configurations to adapt the 2.x gem kernels into the Qt layouts that we require for the 3.0 kernels. So these default gem configurations are essentially lookup tables for things like the tiled MMA, the global memory tiled copy, the shared memory layout, and the shared memory copy atoms, as you can see on the right. Right below that is the CUTLASS 3.0 main loop API, where we can select which main loop we would like to execute. A main loop is principally a collective of threads working together and potentially synchronizing. And we provide a library of these main loops, which include predicated main loops, non-predicated main loops, pipelined main loops for Volta, which pipeline through shared memory and registers, pipelined main loops through Ampere, which pipeline in shared memory, and of course, the upcoming Hopper main loops that we will provide. These are dispatched to via dispatch policies, and so it's very easy to write your own dispatch policy and start constructing your own main loops. There are two primary stages to the main loops, and it's convenient that the code is short enough to put on a single slide. In the first stage, we simply partition the input data for the tiled MMAs and tiled copies, which we reviewed in the Qt section. We can see the stages. First, partition the global memory and shared memory with respect to the thread-sliced global memory tiled copy. Second, partition the shared memory with respect to the thread-sliced tiled MMA and create register tensors. Third, repartition any shared memory and registers for any non-identity shared memory tiled copy. And then prime the pipelines for the main loops by simply calling copy on the appropriate tensor views that we've constructed. It's important to note that almost every object here is a Qt layout or a Qt tensor. Then, the actual main loop. I'm showing the full pipelined Ampere LDGSTS main loop on this slide. It uses N pipes in shared memory to overlap asynchronous LDGSTS copies from global memory. These loads are vectorized and bank conflict free when we've properly designed the tiled MMA and shared memory layouts. Again, there are no tiled iterators here, only Qt tensors, and we have found this code to be much more reliable, extremely easy to get correctness, and the procedure for optimization is simply choosing the best tiled MMA and shared memory layouts in order to achieve optimized global memory and shared memory access patterns. So let's wrap this up and talk a little bit about what we've seen today. On the CUTLASS roadmap, CUTLASS 2.10 was released in August 2022. CUTLASS 2.11 is available as of October 2022. And the CUTLASS 3.0 preview will be available as of November 2022. We've seen the CUTLASS Python API and programming model for constructing CUTLASS kernels and shown that that's interoperable with NumPy with very good performance. We've seen a lot of CUTLASS 2.x enhancements, including the Fuse softmax, layer norm, and multi-head attention kernels that offer significant speedups. Grouped and depth-wise separable convolution reduces the time complexity of certain convolution workloads. The StreamK dynamic scheduling algorithm achieves load balance and reduces the kernel selection burden. And the NVIDIA Hopper architecture enablement accelerates FP64 and will support FP8. The CUTLASS 3 preview, we've shown a new programming model for tensor cores that are based on the Qt layout algebra and metaprogramming abstractions. We implement optimal computations using 4th generation tensor cores in Hopper 100 chip. And this will be released and available in November 2022 to coincide with CUDA 12.0. Thank you for joining us, and see our GitHub at NVIDIA/CUTLASS.